How's everyone going tonight? It's I think my first day back after the New Year's. Maybe not the New Year's, but since I've been back at work in the new year. I think we left off last time on the Chernobyl level. We're gonna pick it up there. I got all of the code into a binary format that we could load into Binary Ninja. The code is a lot more this time, which is why I was doing that. It's just a little bit easier to work on than in the browser, where I don't get things like control flow graphs and pretty much like control flow graphs are the big one, or notes. So I'm gonna head back over to my desktop, show that. I'm gonna get out of this inception a little bit. Like I said, we're in Chernobyl. The big thing we saw here was that there's a hash table. There's two commands we can run here. So we do a reset and we continue here. It's gonna prompt us for access here. Pin. We can see here. This is the run function. This is what's actually running right now. And we can verify this. Actually, it's a little hard to verify it because we don't have a backtrace that we can use. But I'm gonna switch this over to I think to disassembly view. I'm not sure yet. We might do this in the high level IL view, which in Binary Ninja is more or less a decompiler. It doesn't decompile to C, but it's similar to what you'd see from like a high level language. But I guess we can take a look at it. So you get a lot of the same like high level language kind of like constructs. So we have like for loops, we have if statements, else, the typical things you'd like see in terms of flow control and function calls are more or less like what you get here. So we can see here that it's going to print this stuff. Welcome to the lock controller. You can open the door by entering, and then it just prints like a empty line, I think, here. Is it not A? Display as. Is it not? Huh. I thought it was just like string, but maybe it's not. I wonder if like, yeah, that's not what I want. Anyway, trying to figure out how to make this a string because this is what ends up getting called or printed. But let's see what's going on here. So we have an infinite loop that runs forever, and this basically is just like reading our input and then trying to execute what it does. And this is signed decimal. So R14. So this might be a pointer and not actually a yeah. So what this is doing here is it's checking if it's bigger than this. And if it is, this is where everything's getting read into. It takes this, it adds that to the pointer of the beginning of this string, and it adds a null byte. So it's basically just null terminating the string. And then it sets R14 to R14 plus 1. So this is just keeping the length of the current string. Interesting. I wonder if this is going to end up being related or not. So if we don't need to extend the string, we call getString, and it's going to read in a line. And then inside there, we're going to check if it's null. And if it is, we're going to break. We don't really care about that. We're going to check if the first byte is A, starts with A, which would correspond to the access your name pin. If I do this, we go to business display. Yeah, so where it actually matters is right here. And if we go to high-level IL, it looks like it doesn't bring it into here, which kind of is unfortunate. It's annoying. So the first thing we're checking is if it's A. If it is A, R14 3 equals 7 plus, oh man, all these like variables are just ridiculous. Input all right. What does undo or redo? It's Y, control Y. All right. This ends up being something I don't know is whether or not this is a allocated on the stack all the way or not. So what we can do is we can see that adds, I don't know what number this is. That's, yeah. So that makes sense. So it's allocating this much space on the stack. So 1536. Type the I wonder if this... So, access is what? 1, 2, 3, 4, 5, 6, 7. So it's going to skip over the access part. Name. Oh, come on. Really? You're not going to like put this in the right spot? I don't know why it won't put it on this line. Star. All right. I wonder if... No, we don't want SSA form. Yeah, so that's kind of the annoying part about this, is that so many of these variables, like right here, this is one of the things I don't like about this view, is that like all of these things effectively point to the same thing. Like this is doing some pointer arithmetic, and then it makes this equal to this, but like not important. Hey, Goomba Stomp. Yeah, I'm on Chernobyl right now. I'm going through it, trying to wrap it up. This is the second to last challenge. We've been going through them all over the past couple weeks. Have you played through it before? And so down here, like once we move past the access, we're Yeah, this is like my third time playing it. I never got through the end until now. I think I had started like the first two times I started, I got maybe like somewhere between like 3 and 5 in, and then just like stopped playing. So I started again from the beginning, and have done them all on stream for the most part. Um, there's been like a couple things where I like did it like off stream just because I was working on it then, but yeah, there's VODs of most of it, and I think I'm gonna go back and like do a more just like straightforward like this is like walkthrough of it, where I solve them rather than like going through the whole thought process and taking like the sometimes multiple hours working on like a single one of these. The later ones actually get pretty hard, for being such a simple architecture. So here, like we've skipped past the beginning of the access with the space, and we're basically just iterating, and moving the pointer forward in the name field, and we're looking for either a null byte, because that means that it's malformed because we don't have the pin. It's right here, or we're looking for a space, which is the denoting that we have reached the next token, and it's replacing the space with a null byte, just so that like it doesn't have that extra space when it has to do any like setup. The reason for that, I would assume, is because it's going to use string operations on it, and we need that null byte there to make the strings work. So this ends up being a pointer then to our pin, and let's see if I can just comment this. Tokenizing the name, replace space with null. Yeah, this is one thing I really just don't like about binary ninja is there's a lot of stuff about the UI that just kind of like isn't quite where I want it to be. Yeah, definitely. I think after this we're gonna dive into some other stuff. Maybe more exploitation. Maybe going back to some hardware stuff that I've been putting off working on. I just ordered these RISC-V modules from Pine. I think it's pine64.com. Maybe. Yeah. So some of these are like these RISC-V microcontrollers with Wi-Fi and Bluetooth. So we'll be building some prototyping boards for these. I've got a mill back there, so we'll make our own PCB for it and work on like getting these up and running. I'm looking at these as a replacement for the ESP32 for some of the upcoming work I'm doing. But yeah, I don't know when these are going to arrive from China, but when they do, we'll probably jump into that, see if we can get them bootstrapped and running. So this is all of our parsing code and tokenization code for the name. This is going to go back down, and then this ends up being... that's so weird that it sets this here. So this ends up being like the beginning of the string where the pin is. Oops. What did I just do? This also does some parsing for us. So this parses the pin, terminate line with or null. All right. So I think that these might be lengths. let's see here. Oh fuck! I just keep hitting the wrong thing. That's good to know that does that. So this is going to be C, and so I'm just going back and cleaning some of this stuff up. Is it Y? Type for function run. That's not what I wanted. I want change type. It's capital Y maybe? Car star. All right. So we're basically we're just doing some parsing here. Once we've finished doing the parsing, we have this, and so this equals. I don't know what this does, and we're losing something about it when it lifts this up to the high level IL that we're looking at. So we might have to go back to we might have to go back to the disassembly view and read it there. This might be the hashing algorithm. I'm not sure. Yeah, and then see, like we're losing this. So this is the hash table. And this is actually the pin. Types. Huh. Like, I don't really understand like why it can't fold this and like no, like it should be able to do like a folding there and know that like I don't know. That seems stupid to me. So this is I think -1. Or 0? Yeah, it's 0. So all of our negative numbers in this challenge or in this game are all using 1's complement, which means that to figure out what like the negative number is from the positive or the positive from the negative, you just invert the bits. And this is opposed to 2's complement, which we talked about as well. And 2's complement is what modern like Intel AMD processors use. And so what you do there is you flip the bits and then add 1. So if we were to flip this, it ends up being 0. I don't think it has a way to do 1's complement like built into Binary Ninja, but so we're basically just making sure that the return value of this is not 0. Entry or box, I guess. This is actually 0. And so I guess this command isn't like really like a good answer. I don't know what this is here, but maybe like it's like an error message. Yeah, we'll call this message. So if this returns 0, we end up having no such box. So this is leading me to believe that like maybe we're trying to do a collision of some sort. If we know what the algorithm is and we understand that, like we could theoretically, if a box already exists that we don't know about it, we could iterate through a whole bunch of times, and we could guess if we know the full key space, or we can create a collision and maybe create some like another box that already does exist. So let's keep going and see what we find. So it's going to take the box and it's going to XOR it against this. And this is what we get from like, I don't know, like this. So this is the this turns the pin into some kind of value. So it's like hashing the pin some sort. So it's doing some kind of operation where it's gonna take the box and it's gonna XOR it against this pin. I don't know what this actually returns. We're gonna have to kind of dig into that maybe. Get from table. So this looks like a typical like hash lookup. Basically, it does the hashing operation and then it looks it up in the table and then verifies that the key is correct. But we'll go back and we'll reverse engineer this like for real and make sure. So it does that, and then it ands it with 7 FFF. So what this is doing is masking off the top bit, the very, very high bit, or high set of bits. If we look at like what this mask looks like, let me pop open a terminal. Let's see. So we're doing what, 7 FFF. If we will look at what this is, we end up with 1, 2, 3, 4, 1, 2, 3, 4, 3, 4, and then 7 would be 0, 1, 1, 1. So basically, yeah, we're masking off this because if you and this against anything, all of these values that are set are gonna continue down. Anything that's not set will not be set. But this is always not set, so we're always gonna basically just chop off that high bit. Yeah, so we're gonna mask off a bit. And then so it looks like maybe the pin is what gets returned here. So we return that pin, I would assume, and we're going to see if when it masks that off, if it's 0, we don't have access to the box. If what is this? What is S greater than or equal? All right, we got to switch back to this assembly. That doesn't seem correct. So AMs them, jump not 0, to here, to where? To here. So that's an access denied. R10 to R15. So what is it? So this XORs R15 with R10. R15 is the return value. XORs it with R10 and stores it in R10. It masks that off. It's interesting that. So it's like if it's. That's so bizarre that it would check if it's bigger. If the value is bigger, it's granted. Huh. Oh, I wonder if it just means that if it's like if it's 0, it's if it's null, there's no box because it doesn't return anything. If like what gets to here, so this value, I guess, yeah. So if it's not granted, access granted, but not set up or something like that. Can we not? But not activated. So it's kind of weird. Don't know exactly what's going on here, but starting to make some progress. So if we look down here, this is the part that I think we actually care about. This is the other hidden command that they don't tell us about in here. We look here and so this is just making sure it's not n, and if it's not n, it's an invalid command. If it is n, then we're fine. And the parsing on this is pretty minimal. Like it doesn't really care what the string is. In this case, it's looking to make sure that the first character is n, and then let's see here. Then it goes 4 characters forward. And those 4 characters forward will include our space. So access NXX. We don't really know what the ends are, but I mean. And so n plus, or the beginning of it plus 4 should be space. Oh, that's interesting. It looks like it can be any number past 4. This is a space here, hex 20. Character. So we do n plus n, and then a space, and then we're going to look for basically a null byte or a semicolon to end it. Oh no! So yeah, it is three parts. So this does get us just past the n, or whatever it is, name maybe. And then this basically looks until we find the next space, and makes it a null byte. So it's basically just doing that tokenization again here. Tokenizing the name field. This skips past. All right. And then this is that same operation that we saw up here. In fact, it's identical. Yeah. So this is just this this operation. This is some kind of reversible operation that turns whatever the value is that is at the end into the value that we're going to insert into the table. I don't know what this is. That s greater than or equal. It's such a weird like syntax, and I'm so curious like what that actually means. Maybe like signed greater than or equal, and it's just giving us the I don't know. So basically here it's checking like whether or not so it's checking whether or not we have a 0 coming back if it's already in the table. So this is all that if message user already has an account if it's non-zero, and then cannot have a pin with a high bit set. If 3B. Oh, that's interesting. So we can enter like multiple commands here. That's what this is doing here. Is it allows us to use semicolons to run multiple commands. Which part did you see when we were confused about, Goomba? The part right here, or what? Yeah, I don't know. It must be some binary ninja syntax or some kind of bug in the MSP 430 implementation for this. I'm not exactly sure, but basically, here we're assuming that it's not in the table. I don't know what this is doing, but I think it can't figure out that like this is passing on the stack. Yeah. So I think what this is doing or is confused about is that these should be in here, but I think it thinks that this function is let's see, what does it think it's doing? No, it thinks it's stack based. Maybe it's not actually stack based, and that's what it's confused about. So that's the table. And then R3. And then the R10 here. Like this is the part that's kind of weird. Like I think it is confused. So it is pushing. So yeah, it looks like there's two values. So 13. Yeah, so we can just figure out what these are from here. So R9 is going to have the name, and R10 is going to have the pin. Name, pin. Yeah, so I don't understand why it can't figure out that like this is gonna end up being here, and that this here is gonna end up being there, but whatever. We know what it's doing now. And then this just goes down here, which does this like moving forward to get us the next command. So I'm gonna go back here. We should be able to register an account now. And the problem we're gonna have is we got to figure out exactly what that pin algorithm is doing and like what it's figuring out there, because we're gonna have to make that pin be an activated box, and I don't know if that's like maybe that's why the high bit needs to be set or unset, is that the high bit determines like whether or not the box is in use. Maybe there's like some kind of integer underflow or overflow that we can do based on like that operation there. But so I'm gonna continue. We said that it's 1, 2, 3, 4. I think name is probably what they intend it to be. Test 1, 2, 3, 4. So can't have a pin with the high bit set. Let's go back to here. That's not what I wanted. I want that. I want the dead code listing. This. So give me we're gonna want to go back to the dead code listing just because we had to get addresses. So here basically is this is like the math part that it's doing. So it's very possible that we just need to have like a binary pin. We can't use ASCII for it here, or at least like printable ASCII. So I'm gonna hit reset. Rename test. Oh fuck, we didn't do that. Break. All right. Continue. Name test 1, 2, 3, 4. Continue. All right. So what's R10? R10 is currently 0. To R12. Add R12 to R12. 0, 0. Add R10 to R12. Add R12 to R12. Move 3D1F. What is 3D? 3DF1. Okay, so it moves the first byte into R10. So R10 now has 74. It sign extends it, which shouldn't do anything because it's a 8-bit value. Then it adds FFD0. That's a negative number. What is that? FFD0. Can we do bitwise? That's so interesting that it. Huh. We'll do it manually. FFD0. So that's what 0, 0, F, and what's the opposite of D? D is 8, 9A, B, C. So that's D. So that ends up being 2, 2F, and Yeah, it's one's complement. 2F47. Yeah, you're right. Is there a quicker like head like trick to figuring out the inverted bit on there that is faster than like doing that manually? Like I'm pretty good at going like to like doing that in my head, but like not that fast. And I'm not sure why it didn't flip properly in Ruby. Yeah. I really need to like build like a interactive tool that just like does some of this kind of stuff. I don't do it enough where I need it. I've never put the time in for it. 2F is like I think 47 is, let's see, what is 47? Is that A? 47 is G. That's an interesting thing to subtract. I wonder if it's because it's in hex. So it's subtracting G basically from R10. And it adds R12 to R10. Then it increments R11. And so this is just gonna move over to the next character. And then it moves what's at R11 into R15. It tests if it's 0, which it is not. Compare 3B. Oh. So we're at 4C7A. It's not exactly what I wanted. So yeah, it's checking if this is a null byte. But that's weird that it oh, so yeah, it's back here. And then R10 into R12. I wonder if it's like, I wonder why it would use G. So it doubles the letter. Or it triples it. Quadruples it? No, 5 times. It just multiply. This is just multiplying it by 5 times, right? R10, R12. So then R11 into R10. Sign extend it, doesn't matter. Then we subtract G. Add R12 to R10. $10x. Okay. So I wonder if what we need to do is get the pin that we're submitting to pass whatever, like, I guess we got to figure out what the constraints are with it, but whether we can get something that can fit into doesn't have a high bit set but passes this check. Where is it? Right here. Yeah, I'm so curious what that S greater than or equal is. I wonder if it is signed. So one of the interesting things about this challenge is so it has all the malloc stuff in here. It has this function walk, and nothing calls this. It seems like it's a debug function. And I wonder if we're supposed to like. What's 5D? Yes, you're right. This is 10x because it moves it here, it doubles it, it quadruples it here because it's already been doubled, and then it adds one more of the original value, and then it doubles the 5 times, which gives us 10. So you're right about that. It's funny. I mean, I guess it makes sense that they're doing it this way because there's no multiplication, I don't think, like instruction on this this processor. So this is how they have to implement it from the compiler side. Oh, that's interesting. So here's where they add the G. And do we subtract it? So here's where we add it. Yeah, definitely. I mean, it's a low power micro, so it makes sense. So we're 10xing this. Now, and so this is the interesting part is the pin, how many byte, I mean, it can be as many as we want. This is the part I don't quite understand is like how many, is it keeping a running value here? I guess it is. That's why uh, so maybe not. So move R11. So is it accumulating it in subtracts G. So what happens? So like a space is pretty low. We could do 20 in hex, which is 32 times 10. It's gonna be 140 hex. Let's try this. Continue. Name test space that. R11's at 3D F3. 3D F 0, 1, 2, 3. That's weird. So it's not... Let me retry this. So... R10 to R12. R10 has 0, so this whole loop around is just for zeros. 3DF1. 3DF. Oh, so it does it with the whole string, it looks like. But that's not what we saw here. Thought it was starting with... That's interesting. So 3D 41. Why did it get to 11? (3DF0) we said was 47. So why? So 41 plus minus 47. That doesn't seem right. FFD0. So it was 2F. Two F is 47. It's forward slash. I don't know why I was thinking that it's 47 decimal, which is so 2F is here. Okay, so it is looking at numbers. That makes more sense. Or at least looking at like the like alphanumeric values. So we need to figure out if we're supposed to be here or not. I don't quite get that. What's 31 hex? That's 0. That's 1. Maybe that is the issue, and now we're doing this right. Okay. R12 to R10. Increment R11. 3DF 6, 0, 1, 2, 3, 4, 5. Did I do 3 ones or 4 ones? Oh no, yeah, we're good. Oh, maybe it's new, and that's why. That makes more sense. Okay. Cool. All right. Let's do something real quick. New A, B, C, D. All right. Yeah, so I think that this is some sort of like checksum. So we and so are we gonna end up just keeping a I think we just did 3. So 30 is what's 7B? It's 123. So it would end up being 10 plus 10 times 2 is 20 plus 30, 50, 60. R10 into R12. Oh, but it's multiplying. Okay, let's rewind this and let's go back and try this again. I think I see what's going on. All right. Increment R11 Move R11 into R15. Test R15. It's not, so we would loop around again. So yeah, we've multiplied 1 by 10. And then we move the C is what? C is 13. A is 10. B is 11. C is 12. Which 1 times 10 is 10 plus 2. So I think it ends up being something like this. C++. I think that this is it. And we can verify this. So 1, 2, 3, 4. Object 0. Sum n. Sum plus. I think that 4D2. What is 4D2? 1, 2, 3, 4. Ah. This is... Okay. That's what this does. It turns a... It's multiplying it by 10, so it can turn the values into a 2-byte value that represents like a larger number. It's instead of doing a parse int, it's doing this. That's cool. Okay. Is it this that's the issue though? No, so it is this. I just don't know how to get rid of the 0 there, but that's fine. We know what it does now. This makes sense. It's converting an ASCII representation of a multi-digit number into something that fits into into like the number version of itself, the integer version. All right. So that makes sense. Yeah, so it's basically just what's the C function? It's it's not parsed in C. It's so they don't have to do like a scanf. But there's an actual C function. I believe HI. That's what it is. It's like a very, very simple like A to I function that's probably been or maybe it is just A to I, but it's been inlined. All right, so that all right. So this is an A to I, and what does this mean for us with the pin that's going in? So our hash table ends up being the box to the A to I pin. The high bit can't be set. So the highest that we can get to is 0F. Oh no, it'd be EF FF. We can't go above this value. But that's fine. So largest pin above will set the high bit. All right. So let's new yeah, there we go. New A B C D 1 2 3 4. Let's continue. Let's get rid of that. Great. 0 4 D2. 1 2 3 4. Perfect. So now access A B C D 1 2 3 4. So we have access granted, but our account isn't activated. So now we got to figure out why the account isn't activated. And I kind of have a feeling that the activation is done by whether or not the high bit is set. I'm gonna hit wait there, and now where's our heap? Our heap is gonna be down here, I think. So what we might be able to do is make a name that is long enough that we can overflow this byte, these 2 bytes, and give ourselves something that's activated. We would just need to figure out what that ends up being. So let's see here. We get 1 2 3 4 so 2 4 6 8 10 12 14 16 18. So 18 bytes should give us a name long enough. Let's do continue. Let's do new. So 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18 1 2 3 4. I'm gonna continue. 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18. All right. So Four, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So it looks like it does get cut off. Which is unfortunate. I wonder if that code is like the add to table code will end up truncating it or something. So unable to overflow account name into pin to set the high bit because name is truncated after 15 cars. All right. It looks like we have a lot of space in between these, and we're not going to be able to make a value that's beyond 2 bytes for our pin. Oh, oops. So that's interesting. That's 15, 16, 17, 18. No such box. Huh. Did we break something? Yeah. So that's weird. We can't access the box. It's definitely here. We don't get a deallocate. I don't think. Like I don't see us calling free. Maybe we have like an implicit free that we can use in rehash. So inserting, we can cause an implicit free. And rehash is called during add to table. I'm not sure what this condition is here. implicit free via rehash and add to table. We might need to go into here and like see what it's actually doing. Create hash table. R11. What does... Where's run? So 3 and 5 get passed in. R7. And there's some kind of parameters. Not quite sure what they are yet. Maybe the number of, the initial number of slots that get allocated. That's kind of interesting. I don't know why there's so many allocations in here. We can try adding, let me, where is rehash? Here. So it doesn't seem like the 3 is the number of slots to make. So yeah, I mean, we got to figure out like what this is doing, probably. How we can trigger the free. Like we don't get an overwrite with our name. Where is? Like, I'm so curious about the walk, like what this is for, and like I wonder if we can just move. Um, what the fuck is going on? Oh, we're gonna have a problem because R11. What is this? It's like that's the pointer. Hmm. It's like it doesn't do any allocations. Um, it Like, I wonder if this just walks the heap. But it'd be an R15 is the problem. Is there a way if we can just break immediately? We can just reset. That's fine. New. All right. I'm gonna $15 equals 5,000. Wait. Let PC equal that. Yeah, there we go. So that's what this is supposed to do. Is it walks the it walks the heap, I think. And I don't know that I... Oh, yeah, so here. That's previous, next, size. And what we probably need to do... Oh, so here's a problem. I think all the size values are wrong. Because B5 is like a pretty... Well, maybe not. 5,000... Previous... Uh... 5016. 5016. I fucked up. Oh no, it didn't. Five zero 3C. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C. Yeah, this is correct. It's just the sizes are wrong. And we saw this last time when we were looking at the heap challenges. Like, it says 5B is the size of our... Or sorry, this is B5, but oh, you know what? That is correct. This is our hash table. So this right here is our hash table. And yeah. What's B5? It's 181. Oh, I think we'd end up fucking this up if we do this, but like where are we right now? We're in walk. Yeah, and this is our free chunk. This is our top chunk. It's huge. This must just be here for us to do this visualization. Like this. So there must be something about the hashing function we have to do, or something about the way the tables are created, because we don't get to overwrite. I mean, we can try it again, but we can go down to here to the hash table, and yeah, I mean it puts the null byte there. that's so weird. So like if you look here, these are all like pointing into here. So like I think we said it was this. So this is our next, our previous, and $52C. So I think this is the size field. So the previous, so 51.6. Right here, 4.2. Yeah, so right there. I don't know. I think I'm gonna call it for the night working on this. It's 9:30 now, and about 2 hours in. We made a lot of good progress. We have a really good understanding now of like what's going on. I think we need to basically go in and reverse engineer probably the create hash table function, add table, and maybe rehash. There's a possibility that the implicit free will give us enough control to do something. Maybe like we can get like a double free or something, but I don't know. We clearly don't have an overwrite because it's not letting us write past the end of the allocated space. But maybe there's something we can do where we like get it to give us more space, or it rehashes the table and there's like some kind of coercion where it overwrites somewhere else, or there might just be something we're missing so far. But like we at least kind of figure out the parsing side of things. We know how to like play around with this now. Yeah, we're making good progress. I'm not sure when the next stream is going to be. Maybe Saturday or Sunday. Just got to kind of figure out like what the time is like for it. But I think then we'll be able to get a little bit better look at the heap side of things here and see if we can spot some kind of bug that we can exploit. Anyway, I hope you all learned something. Hope you enjoyed it, and I'll see you all next time. Bye.